In an earlier video, I alluded to what's known as the sodium doublet. So where you see the sodium doublet is it's a pair of yellow lines, and they're referred to as the sodium D lines. The experimental setup is you imagine having, so this is meant to be a glass tube with an extremely low density gas of sodium atoms, right? So there aren't any other structures inside of the glass tube besides sodium atoms. So there's no molecules. There's no other atoms either. That's the idea. So it's this glass tube is empty except for a small number of individual sodium atoms. And what we imagine doing is figuring out how to excite these sodium atoms. So the sort of device is called a gas discharge lamp. You can look this up online to see what kind of thing this is. But anyways, it's a lamp. That is, it glows, and it glows with light. And the light is emission spectrum of sodium atoms, right? No other structures besides the sodium atom system. Okay, so if you look really close at this light, that is, you have to use a spectroscope, right? A spectroscope is a device that might involve a prism, right? So you use prisms to separate the colors of light coming away from some source of light. But in fact, actually, prisms, the typical prism, doesn't actually have the resolving power to show you the two individual yellow lines. A prism will put these two lines too close to each other. That is, it doesn't have good resolution. So not enough resolving power or resolution, right? So you have to use a different kind of device. The device that I've seen used in a laboratory is called a diffraction grating. So you can use a diffraction grating, and the interference of the light coming from our sodium lamp goes through many small slits. And when you overlap the light that makes it through each of the slits, right, there's an interference pattern. And in that interference pattern, you can get these very thin sodium lines. So that's one type of spectroscope device that does have enough resolution if you have very narrow slits and many of them, so you get a nice bright signal. Or there's a very special device. It's a piece of, it's an optical instrument, just like the diffraction grating and the prism are. It's called a Fabry-Perot interferometer. And this thing is very special. It's very nice. You can look up what a Fabry-Perot interferometer, or how it works if you'd like, and you can look up diffraction grating if you'd like. But the point is you have to have a spectroscope to separate the colors of light. And if you look nearby where the yellow light would go in your spectroscope, you're going to find two very well-defined sodium D lines, and these things are going to be pretty bright. That is, there are lots of photons associated with these two lines. But the truth is if you scan around in the light that makes it out of this sodium gas lamp, you're actually going to see a lot of visible wavelength doublets. You're going to see a visible wavelength doublet for red, but it's not going to be as bright. You're going to see a visible wavelength doublet for green, but it's not going to be as bright. And you're going to see a visible wavelength doublet for blue, but it's not going to be as bright. the yellow is by far the brightest. So the sodium D lines are very bright. But the red, not yellow, green, and blue doublets are more dim. Okay, so here is some physical data, right? And this is something that an observer will see this, right? This is observable. Oops. So observable, right? This is an observable phenomenon. And the question is, what's the explanation, right? That is, what sort of physical theory can explain this thing we can go and observe? And the answer, of course, because you're studying quantum mechanics, is quantum mechanics, right? So what I've been telling you so far, the sort of last topic was this spectroscopic notation topic, right? Spectroscopic notation. So we are studying sodium, and we have a way of understanding the electronic structure, right? How the electrons are distributed in sodium atoms, right? Electrons are distributed, and that's what the spectroscopic notation describes for us. And so let's write down sodium's ground state. Oops. Okay, so the sodium ground state. So the sodium ground state looks like the following thing. If you look at a periodic table of elements, and you've been looking at how to build up spectroscopic notation for the ground state for various atoms, you can see that what you'll build up is this core and this valence. So this is the core of the atom, and it's mentioned, or it's described as the core because that is the noble gas atom. Oh, I guess I didn't write it down, but I think it's argon. But anyways, so this is the noble gas atom, and it's not, yes, noble gas atom, element. And then this piece right here, which is sort of the incomplete shell, these are complete shells. This is the n equals to 1 fully full shell, and this is the n equals to 2 fully full shell, right? So all of the L numbers are covered for n equals to 2. So L equals to 0 and L equals to 1. That's the S and the P. And n equals to 1 only has one L value. L equals to 0. That's the S. So n equals to 1 and n equals to 2 are fully full. But the valence shell is the outermost shell, and it is not full for sodium. Okay, so so this kind of gets us to think in terms of a core. So I'm going to kind of shade out the core with, I guess, black, right? So I've got this core. That's the noble gas aspect. And then I have this single electron that gets to exist outside. In a sense, it's outside. So this is my electron lives here, right? Or at least the valence electron lives there. But I've got this core, right? And the core, if you think about it, right? So I've got a neutral sodium atom. That is, I've got the same number of protons as electrons. So the core has a charge of plus E. So I've got this core, right? And then I've got this lone electron out here in this s orbital. Okay, now this electron can be spin up or it could be spin down, right? And we actually don't have any reason to know whether or not, or care actually even, whether or not the electron is spin up or spin down. But those are the two options. The electron can be spin up or spin down. Okay, so this is all well and good, and this is a picture of the ground state, right? So, okay. So up here in this sodium lamp, what I'm saying is you get this light not because of sodium atoms in the ground state necessarily. What's happening is as you excite these sodium atoms, a sodium atom becomes excited. So I put this little star, and then some time passes and it's an unstable sort of energetic configuration because it has the option of existing in a lower energy. So that's the sense in which it's unstable. And so what's going to happen after some time is that excitation goes away, and because of energy conservation, right, we need that energy to go somewhere, exist somehow. If the sodium atom doesn't have it anymore internalized to itself, then that photon heads away. And that's one of the photons that's coming out that we are inspecting with the spectroscope. But, you know, there's a lot of photons coming away, right? And that's why this thing's glowing. Some of the photons are this yellow, and some of the photons are this yellow, and some of the photons are this green, right? So these photons distribute themselves across these colors, but you only get very particular reds, very particular yellows, very particular greens, and none of the colors in between, right? So there's this very quantum mechanicalness to the energy, the energies available for transition, right? You get this discrete spectrum. Okay, so it's about having excitations, right? And the de-excitations are the emissions of photons. So this is the ground state. This is the lowest energy. And the question is what are some higher energies? So higher energies, the way we imagine this is we imagine only changes to the valence electrons. For sodium, there's only one valence electron. So in the ground state, that valence electron lives in the 3s subshell. So we only imagine changes to the valence electron. So a higher energy, right? We could imagine the sodium being not this configuration here. This is the ground state configuration. But why don't we imagine a different subshell? So we could imagine, for example, the core, right, which was 1s2, 2s2, 2p6, and actually, yeah, let me actually just so we'll just add, oops. Okay, so it's the core, and instead of 3s1, let's put it in a p orbital, right? And what's interesting about this is if the atom, this is an excited state atom. Sorry, I had to move some cats around. So back to this. So what I just drew for you is the electron configuration, right? Quantum state configuration of an example excited sodium atom. And so what I'd like you to imagine is so if this is what the ground state atom looked like, then what does an excited state atom look like? Well, if it's excited, that means the electron may spend a little bit of time further away from the nucleus, maybe sometimes moving faster, right? That's what's meant by having a higher energy, is you can have the opposite charges separated a little further. So I'm going to imagine drawing, right? So this is something of a semi-classical sort of approximation or conceptualization. But up here I had this core. We're only making a change to the valence, so the core stays the same. It's still charge plus E, right? But now, in a sense, I've got my electron existing in a 3p orbital. I put the little 1 because I only have one electron, right? Okay. So p orbitals, they are the L equals to 1 orbital, right? So p orbitals are the L equals to 1 orbital. And this means that we can have angular momentum associated with the swirl of electrons, right? So I have a swirl of electrons. Let me actually write this more clearly. Swirl, right? So the electron is actually got an overall swirling motion around the nucleus or the core. Okay, so if that's the case, then this electron, and I'm going to draw it in a strange place. I'm going to say that it's just here, for example, right? So that's that 3p1 electron. It's in here. But I've got this swirl. And what I'd like you to realize is that if you have a swirl of electrons, then what you also have is magnetic field. So I'm putting in a magnetic field, right? So this magnetic field I'm going to say it's due to orbital angular momentum, right? It's due to this electron swirl, right? But you also know that the little electron is itself a little magnetic dipole moment. So I've got magnetic field, right, due to orbital angular momentum. And because the electron is a little dipole moment, this is the electron is like a little compass needle, right? The electron's a little tiny magnet. So let me remind you of something that's sort of some basic physics. If you have a magnetic field, right, this is the way you can sort of test for the magnetic field is by putting a compass in it, right? So if you put a little compass needle, right, so that's just a little compass with a north pole and a south pole, the compass tends to align with the field, right? It feels a torque such that it tends to align So little compass needles, right? So compass needles tend to align with magnetic field, right? So that's how you find your way around the Earth, is you use a compass and let it align with the Earth's magnetic field, and use that alignment to, if you want to walk west, you have to figure out how west is related to north, but etc. So that tendency is energy, right? There, and so something that you would have learned in a previous course is that there is a potential energy associated with the relative alignment of magnetic field and magnetic dipole moment, right? It's the relative alignment of the compass needle and the background magnetic field. And that potential energy comes with a minus sign, and it looks like this. And this mu thing we can understand as spin, and this B thing is because of orbital angular momentum. And this energy is spin orbit coupling. All right? So, oops. Okay, so spin orbit coupling energy. All right, so here it is. I've got orbital angular momentum associated with the swirl of electrons, and simply because our little electron is a little tiny compass needle, a quantum compass needle, there is going to be energy there. So I've got this excited state. The excited state could be the electron is spin up in that excited state, or the electron is spin down in that excited state. But the thing about this is there is a background magnetic field, right? So I've got this background magnetic field, and my little electron can either be spin up or spin down. And being spin up or spin down is a difference in energy. And what that does is it gives us an energy level diagram. That is, if you look at the 3p level, right? So the energy level diagram, right? You've got the, I don't know, in a rough sense, you have the 1s and the 2s and then the 2p, like this. And then you have the 3s. Let's see, yeah. And then the 3p level is here. So this is the lowest energy, and higher energies are above. So these, right? So if you go out to a larger principal quantum number, you're talking about larger energies inside the atom's electronic structure, right? So here's the 3p level. Okay, so here's the thing. So what we just learned is, because of spin orbit coupling, there's going to be a difference in energy based on whether or not the electron is in alignment with the magnetic field or against alignment with the magnetic field. This is essentially the idea. So there are actually, in the 3p level, there are actually two slightly different 3p's. The upper 3p is because the electron is spin up, and the lower 3p is because the electron is spin down. What's interesting about the S level is S is the situation of no orbital angular momentum, which means there is no background magnetic field, which means that spin up or spin down have the same value of energy, is the idea. But the 3p level, or the subshell, the 3p energy is actually split. This is a small split. And the difference in energy between the two levels, the difference in the energy is really small. It's only 2/1000ths of an electron volt, right? It's like 2 milli electron volts. So it's really small. Okay, so let me go and erase. There's not 2 electrons here. There would only be ever 1 electron if that valence level was filled, right? So here now is the origin of those 2 different yellow lines. So here are these 2 different yellow lines. They have slightly different frequencies, which is why our spectroscope separates them. They have 2 different energies. And those 2 different energies are from here. So that is the higher energy yellow line, and this is the lower energy yellow line. Those 2 yellow lines are coming from the 2 different p orbitals, or the p subshell quantum states. And those 2 p subshell quantum states are different because of spin-orbit coupling, right? Okay, so we're sort of tying together lots of interesting ideas. Okay, so this is the explanation of the 2 yellow lines. What's interesting is to wonder, what's the explanation for the other colors? There's a, oops, let me quit using yellow there. There is this red doublet, there is a green doublet, and a blue doublet. And they are not as bright as the yellow. The yellow is super bright, but the green, red, and blue doublets are not as bright. But what I'm going to show you is where these other doublets come from. The other doublets come from transitions from other s orbitals, like 4s, 5s, and 6s. Notice that I'm drawing each next energy level, and I should have actually, let me make it really very obvious. So the 1s is really far away. So the separation in energy between an electron being in the 1s or the 2s subshells is really large. The separation between the 2s and 3s is a lot smaller than the 1s and 2s. And then actually I should have drawn all of the 4s, 5s, 6s much closer to the 3s. Okay, so anyways, here are the origins of those other colors. Red is the lowest of the energies between red, green, and blue, right? Red is the longest wavelength, lowest energies. And those 2 red lines come from the single energy level in 4s, spin up or spin down, can either go really far to the lower of the 3p's or not quite as far to the upper 3p. So those are the reds, that's the red doublet, and they're slightly different in energy. The greens come from above, from 5s. So the greens can go down to there or here. And the blues, actually I used a darker blue, so they come from there. And so all this is to say, the electronic orbital model, so the S, P, D, F, etc. choices with the various principal n values, right? If you mix this with some basic magnetic field physics and magnetic dipole moment physics, So mix this with basic B field and magnetic dipole moment physics. What this does is it gives you predictions. You can predict or explain the doublets, right? So there is one other thing that this actually explains, one other detail that this exploration explains. And it's a physical detail, right? It's something that you can take data on. It's the fact that the red, the green, and the blue are dimmer. That is, there's not as many photons for each of those colors. But the sodium lines are really, really bright. They're overwhelmingly bright. Notice that I drew the glow of the sodium lamp as being mostly yellow looking, right? Because it's overwhelmingly yellow. But there is some red, green, and blue in there as well. And the interesting thing is if you look at this diagram, also explains the relative brightnesses. And the way it explains it is the following. If you see blue, you're going to see yellow, right? Because if the blue transition happens, it's from 6s to 3p, then what follows that is a further transition to the ground state. That is, if you see blue, you see yellow. But if you see green, you see yellow. And if you see red, you also see yellow, right? So anytime you see blue, you're also going to see yellow, but you're also going to see yellow anytime you see green. So the point is in a sense, the yellow transitions are 3 times as bright as any of the individual blue, green, or red transitions. That's the relative brightness. Yeah, I think that's incredibly interesting. Like, it's a very simple explanation of the relative brightnesses. But yeah, you can imagine like the experimenter's surprise. A long time ago, they're like, well, let's make a sodium lamp, and then let's use one of our new special tools to look at the spectrum. And they look really close, and they're like, holy smokes. We thought these were all single lines, but they're actually doubles. I wonder what physics tells me that. And not only that, it's still that the yellow is overwhelmingly bright compared to the other colors. I wonder what physics tells me that. And then Schrodinger comes along, tons of other smart people come along, solve some math problems, think a lot, conjecture a lot. And they're like, well, magnetism's still important. We've got this strange feature called spin, and lo and behold, you get this kind of energy level diagram structure, and it predicts for you the doublets, first of all, and then it predicts for you the relative brightnesses, right? So that's pretty convincing sort of thought process that what you're onto is something that's fairly correct. Okay. Thanks.